expectation and variance for continuous random variables. This is really, really great stuff. The expected value of a random variable x is, if x is discrete, it's this stuff. You already know this, right? It's a weighted average. Here, you're averaging all the possible values x can be against the probability weights, right? So that where this part is this is your probability part, right? Actually, this is your probability part, right? And then this is the summation sign. Of course, this is just how you take a weighted average. Similarly, if x is continuous, if x is a continuous random variable, then this now is the probability part. See that? And then this is the summation sign, right? That means to add up. And then this is like that. Okay? You see that? Now, technically here, and I'll do this over to the side, if we write f of x dx, this is the probability that the random variable x takes on a value between x and x plus dx. Okay, it's the chance that you see x in a small neighborhood there of the point x. Okay, so that's why this is the probability part. If I take the density times dx. Okay. All right. More generally, though, it turns out actually, if I had I could write either of these cases like this, where the df here, this is telling me the size of the jump, if there is any, of the CDF. Okay. See, so that if there's a jump there at the CDF, then this has a non-zero weight to it. Otherwise, if it's a continuous, if it's got a continuous part to it, then it's just the density times dx. We won't really consider these cases in this class. Maybe we might see one or two problems here and there, but for the most part, we'll stick to purely continuous or purely discrete cases. So let's do an example here. Again, let's use that density function that we had before, where we had f sub x of x was equal to, what do we get, 3/8 times x squared times the indicator of x being between 0 and 2. So, if I want to find the expected value of x, then I know that this is just going to be the integral over the reals of, let's see, I take x and then times its density dx, right? Okay, so then this becomes the integral over the reals of x times 3/8 times x squared times the indicator of x being between 0 and 2 times dx. Okay. Now, so this is just it's going to be 3/8 times the integral of x cubed times, hey, you know what? I can get rid of this indicator function. It's 1. All this is going to be 1 if x is between 0 and 2. It's going to be 0, making the whole integrand 0 if x is outside of that closed interval 0, 2. So I'll just integrate from 0 to 2. Right? Get rid of the indicator function. I love indicator functions. I love them. Just the fourth, or 4, 0 to 2. Let's see, what does that spell? 2 times 2 is 4 times 2 is 8 times 2 is 16. Over 4 is 4. I think that's 12/8, isn't it? Or something. What does that reduce to? I don't even know. 3/2. Okay. Very good. Let's see if we can do another one here. What about the variance? Guess what? The variance of a random variable is still defined to be the expected value of the square deviation from average. Okay. same as it was in the discrete case. Same as it was in the discrete case. And you can still show, using the same steps as you've done before, that this is equal to expected value of x squared minus the expected value of x quantity squared. We call this the inside-outside formula because the 2 is on the inside here, minus outside. Get it? Okay? Yeah, it's the same kind of thing. And also, for the continuous case, if g is a function that takes the reals to the reals, say, then it turns out the expected value of g of x is just the integral over the reals of, guess what, g of x weighted against the probability part, which is the density of x times dx. Okay? Great. So back to our example. Can we get the variance of x? Sure. It's going to be the expected value of x squared minus the expected value of x quantity squared, right? I've already got the mean. The mean was 3/2. So I just need to get this part. Let's see, the expected value of x squared. I know how to do that. This formula up here tells me how to do it. See, I recognize the square function here. That's going to be my g. So I'll put x squared there, and then weight against the probability part. Ah, genius. There's x squared indicator over the reals indicator 0. And, yeah, very good. That's right. Oh yeah, and then minus 3/2 squared, right? Okay, good. So this works out to be, I guess this will be 3/8 times x to the 5th over 5, and then from 0 to 2 minus, 9/4, I think. And so this is going to be 3/8 times 2 times 2 is 4 times 2 is 8 times 2 is 16 times 2 is 32. Okay, and let's see, what does that turn out to be? I think it turns out to be 0.15. Is that right? I don't know. You can check it. I've lost my calculator. Oh no, here it is. 3/8 times 32 over 5 is that, minus 9/4. Excellent. Look at that. Got it. What's the CDF? What's the CDF? What is the cumulative distribution function? Find the CDF. Oh, goodness. So let's let x take a value in the interval that's interesting here, 0 to 2. Because actually I know what the CDF is going to be outside that interval. If it's to the left of this interval, the CDF is 0, and if it's to the right of this interval, it's 1. Think about that for a second. We'll come back to it here in a minute too. But if x takes on a value there between, actually, let's make this a little x. If little x takes on a value between 0 and 2, then my CDF, remember, this is going to be the integral from negative infinity up to x of my density function, right? And I've got an x there, so I'll take another variable for my dummy variable there. And so this is actually from negative infinity up to x. What was my probability density function there? It's 3/8 times x, s squared, right? And again, I'm using an s there instead of an x because I've got an x up here, okay? That would still be okay, but it looks kind of dumb. So I'm going to put the indicator function like this, right? X between 0 and um, 2, right? S ds. There we go. So what is this? Again, so now I can look at this. X is somewhere between 0 and 2. I think you should see that this just turns out to be this, 3/8 s squared ds, right? If x is between 0 and 2, then I don't have to go any farther up than x. I have to stop at x, in fact, right? All right, so what does this turn out to be? This is going to be 3/8 times s cubed over 3 from 0 to x. This is going to be x cubed over 8. But that's just for x between 0 and 2. So the CDF is, we've got 3 regions here. We have to be real careful. We've got 3 regions. It's going to be 0, or it's going to be x cubed over 8, or it'll be 1. It'll be 0 for x values that are less or equal to 0, and it'll be x cubed over 8 for x between 0 and 2, and it'll be 1 for x greater than 2, right? Good. By the way, what's the median of a random variable? Let's graph this CDF function. Here's one. So let's see. So if x is, so here's the x-axis, and so this CDF is 0 down here, and then once it hits 0, it's going to look like x cubed over 8 until we get up to 2. My x and my horizontal and vertical axes are not on the same scale. I hope that's okay with you. So this is going to look like it's going to look like this. It'll look something like that, and then continue on like this, right? Yeah. All right. Where's the median? Well, the median you can find if you graph the CDF and then find 50%, and then if it's a continuous variable, it's easy. You just walk out to wherever that line here at 50% hits the CDF and then drop down. So it's going to be here. Here's your median. Okay, that is the median for a continuous random variable is going to be the place. It's going to be f sub x inverse, the inverse of 0.5. Okay.